This theorem is very important because it is the first step that we need to prove the fundamental theorem of arithmetic, which we'll show in the next video, which states that if we have any integer that's not equal to 0 or plus or minus 1, we can write it uniquely as the product of primes. What this theorem is telling us is that we can write it as a product of primes, and then the fundamental theorem of arithmetic, we will prove the uniqueness. So first, let's assume that n is strictly greater than 1. And what we're going to do is we're going to define a set S. So let S be the set of all integers greater than 1 that are not the product of primes. So the strategy of this proof is to take this set S, which is the set of all integers that are not the product of primes, and show that it has to be empty. This would give us that that all integers greater than 1 are the product of primes if the set of all integers greater than 1 that are not the product of primes are empty. So how do we show that it's empty? We're going to do this by contradiction. So first we suppose that it's non-empty. Now everything in S is an integer greater than 1, and so we know by the well-ordering axiom that S must have a smallest element. And let's give that least element a name. Let's call it M. So what can we say about M? Well, we know that M is not the product of primes, so in particular, it can't be prime itself. So since M is not prime, it must have some positive divisors. So we can say equals A times B for some positive integers A and B. And what do we know? We know that M is the smallest element of S. So what can we say about A and B in relation to M? In particular, they both have to be strictly greater than 1 because it's a set of all integers greater than 1 that are inside of S. And we also know that has to be strictly less than M. And actually, I misspoke. So the reason that A is strictly greater than 1 is because we're assuming that M is not prime. So M has factors that are not 1 in itself. And we're choosing 2 of those factors to be A and B. So that means that we can bound A by 1 and M. And similarly for B. But if we have A and B strictly less than M, which is the least element of our set, then A and B can't be in S. And so, what does it mean for A and B not to be in S? S is a set of all integers greater than 1 that are not the product of primes. So if A and B are not in S, which is a set of all integers that are not the product of primes, then that means A and B must be part of the set of integers that are the product of primes. So we know that A and B must be the product of primes. So we can say that A, let's see here, A is equal to P1, P2, times PR for primes P. And similarly, we can write that B is equal to Q1 times Q2 all the way up to QS. And so what do we have here? We note that because A and B could be prime, so we're going to have that R is greater than or equal to 1, and S is also greater than or equal to 1. And each P sub I and Q sub J is prime. But then what does this mean? This means that we can rewrite AB using the product of primes that we have here, which means that we can rewrite M. So that gives us that M equals AB equals P1 times P2 times PR times Q1, Q2, QS. And that tells us that M is a product of prime numbers. But M, where did it come from? Remember, we have this set S that is characterized by the fact that it contains all of the integers greater than 1 that are not the product of primes. M is the least element of that set, and so we can't have it being in that set and being a product of primes. And so we've arrived at a contradiction. So if we assume something to be true and it leads to a contradiction, that thing cannot be true. What we assumed was true here was that S was a non-empty set. And so what this tells us is that S must be empty. So if we take all the integers that are greater than 1 that are not the product of primes, we get an empty set. So that tells us that every integer n greater than 1 is a product of primes. And this argument also holds for negative n as well. And so we have the first step that we need to prove the fundamental theorem of arithmetic.